Hello, this is Utstochi Caleb from Special Maths Academy, and today we'll be solving the recently concluded PAMO 2022, the problem 2. So here we are told to find all A, B, C, A greater than B greater than or equal to C, such that A squared plus 3B, B squared plus 3C, and C squared plus 3A are all squareds. So basically we have A squared plus 3B is equal to some X squared, B squared plus 3C is equal to some Y squared, and C squared plus 3A is equal to some Z squared. Of course, X, Y, Z are all positive integers, right? So basically this is what we are given, and we are told to find all possible three tuples A, B, and C, right? So the natural way to go about this, the best way to go about this is to try to bound A, B, and C, right? So and we have already been given a very nice inequality here, which is A greater than or equal to B greater than or equal to C. And then having this in mind and also looking at the squares in play here. So the natural way to handle the case of, let me put that separately. The natural way to handle a case of, let me say, P squared plus some T is equal to Q squared, is to say, okay, that's T in this case is a natural number, is to say so P squared is less than Q squared, and this implies that P is less than Q, right, where they are all natural numbers. So and then you now try to make Q less than some other square, or you try to make Q squared less than some P plus, let me say, R squared. Then this now implies that P less than Q less than P plus R. So this is a very popular technique and a very natural way of going about when a square is equal to some other square plus a natural number, right? So we'll try to do that here, and we are going to utilize this inequality, A greater than B, A greater than or equal to B greater than or equal to C. So let's take A squared plus 3B is equal to X squared, for example. So we are going to have A squared less than X squared, since B is a positive integer, so A squared is strictly less than X squared, and of course X squared is equal to A squared plus 3B. Now this is where this inequality comes in now. So A greater than or equal to B, or B less than or equal to A, implies that 3B is going to be less than or equal to 3A. So this is going to in turn imply that A squared plus 3B is less than or equal to A squared plus 3A. Now this is where this technique is coming in, where I say we now have to, when we have something like this, then we'll set P squared less than Q squared. Then we'll now try to show that Q squared is less than some P plus R squared, and that is going to force Q to be between P and R. So now we are not going to try to do this. We want to show that X is less than some X squared, is less than some A plus R squared. So now this is now going to force A less than X less than A plus R. And then that's the bounding we want, because X is equal to A plus 3B. So let's try to do this. Let's start with R equals to 1, for example. What is A plus 1 squared? A plus 1 squared is A squared plus 2A plus 1. So A squared plus 3A is not strictly less than this. Let's try A plus 2 squared. Now it's more like we are trying what to use now, because we want to get this inequality here. So let's try A plus 2 squared. A plus 2 squared is A squared plus 4A plus 4. Now this works, right? Because X squared plus 3A is strictly less than a squared plus 4a plus 4, and you have a plus 4 as change, right? Which is definitely a positive number, right? So we can now force now this to be less than a squared plus 4a plus 4, which of course is equal to a plus 2 squared. Now we now have the inequality I was looking for, or we were looking for, and what's that? Inequality I was looking for, and was that we have a squared is less than x squared, which is in turn less than a plus 2 squared. Now this is a very nice inequality to have now, because they are all positive integers there, right? So this forces a to be less than x less than a plus 2. Now of course the only possible solution for x now would be x. Since x is an integer, the only possible solution for x would be x equal to a plus 1. Now you guys have seen how the bounding has helped us in this case, right? So now basically what is x? We have x, so x is x squared is equal to a squared plus 3b, right? So let's square this. We have x squared will be equal to a plus 1 squared, which is a squared plus 2a plus 1. And of course this implies that a squared plus 3b is equal to a squared plus 2a plus 1. Then this gives us that 3b is equal to 2a plus 1, right? And you can also rearrange the coefficients or variables per se. You arrange the variables to give us a is equal to 3b minus 1 over 2, right? So now I've gotten a as a function of b, or a in terms of b, or you can put it as b in terms of a. Now this is very important, right? Because it will help us a lot in finding the all three tuples, right? So now let's, of course, we still have we remember we just used a greater than or equal to b in this case, and we still have b greater than or equal to c, right? Unfortunately we don't have c greater than or equal to a, it's the opposite, but b greater than or equal to c is very nice to have. So we can do a similar something with that and say b squared is less than y squared, which is equal to b squared plus 3c, which is less than or equal to b squared plus 3b, which is less than b plus 2 squared, right? And then this implies that b squared less than y squared less than b plus 2 squared. So now this is going to imply that b is less than y less than b plus 2, which in turn implies that y is equal to b plus 1, which implies that y squared is equal to b plus 1 squared, which implies that b squared plus 3c is equal to b squared plus 2b plus 1. And then this implies that 3c is equal to 2b plus 1. So now we have c in terms of b, right? We can express this as this c is equal to 2b plus 1 over 3. Now we have a in terms of b and c in terms of b. So if for instance now we had c less than or equal to a, for example, we can do this again and maybe get a and c in terms of each other, but we don't have that, but we are still fine, right? So we find out because we have a in terms of b and c in terms of b. So how do you go about this now? We use bounding to get a in terms of b and c in terms of b. So how do you go about this now? We still have a third square, right? And that is c squared. That is c squared plus 3a is equal to z squared. Now I want to bound C as well. We bounded A, we bounded B, we want to bound C as well. So we are looking for something similar to this, but we don't have C less than or equal to A. So maybe we have to be more smarter about things. And a good way to go about this is to substitute B, to substitute C in terms of B and A in terms of A, and we'll have something like 2B plus 1 over 3 squared plus 3 times 3b minus 1 over 2. Let me confirm that. Yes, A is equal to 3b minus 1 over 2. And this is going to give us a square, right? So now we can simplify this, and then we'll now get some quadratic expression equal to z squared. Then we can also in a similar fashion that we did here. Here was that. In a similar fashion that we did here, we can now bound C, right? The same way we bounded A and B. So that's what we are going to do, right? But we can be smarter about this. Why? Because using 2b plus 1 over 3 and 3b minus 1 over 2 are going to bring in a lot of fractions, right? And working with fractions is not efficient. So we want to eliminate the fractions as much as we can. So to do that, we'll have to maybe express B as something, or B as maybe, let's say, for example, for this, we want to express B as maybe something K plus something, so that the 3 cancels out. And to do that, we'll have to go back to what we got, and that's 2b plus 1 equals to 3c, right? So now 2b plus 1 equals to 3c is going to imply that now 3c is a multiple of 3, right? So this is going to imply that 2b plus 1 is equivalent to 0 mod 3. Now remember, I'm trying to express b as maybe some rk plus, or let me say rk plus s, such that when we substitute rk plus s for b, now the fractions are going to cancel out. That's what we are trying to do now. So of course, if you are talking about a fraction of 3 and the denominator 2 cancel out, you are going to be looking at mod 3 and mod 2. That's why I'm bringing in 2b plus 1 equals to 3c, because that's going to give us what b is in mod 3. And similarly, we can use the second expression, which is 3b equals to 2a plus 1, to give us what b is in mod 2. Now using mod 3 and mod 2, we can get b, we can express b as some rk plus s, and which is going to eliminate our fractions. Well, that's what we're trying to do. We can go directly from here, but to be more efficient, we can do this as well. So now let's finish this up. We have 2b plus 1 is equivalent to 0 mod 3. So this implies that 2b is equivalent to minus 1, or as well 2 mod 3. Now 2 and 3 are relatively prime, so we can cancel 2 out to give us b is equivalent to 1 mod 3. Now this is nice. We have what b is in mod 3. Let's also try to get what b is in mod 2, right? So I think it's best to write this as 3 divides b minus 1, right? Okay, now let's keep that aside, then try to work with mod 2. Remember also we have that 3b is equal to 2a plus 1. So this is going to imply now in mod 2, remember that 2 divides this. So this is going to imply that 3b is equivalent to 1 mod 2. Right? So again, again, of course, we can. This is going to imply that B is equivalent to 1 plus 2. We can always outright, since we are working with mod 2. Mod 2. So this is going to imply that 3B is equivalent to 3 mod 2. And again, 3 and 2 are relatively prime, so we can get that. We can cancel 3 out and get that B is equivalent to 1 mod 2. Now this is going to imply that 2 divides B minus 1. Now we have 2 divides B minus 1 and 3 divides B minus 1, and 3 and 2 are relatively prime, right? They are primes. So this is going to imply that 3 times 2, which is 6, divides B minus 1. And of course, this implies that B is equivalent to 1 mod 6. So now this implies that we can express B as 6k plus 1 for some k greater than or equal to 0, right? Also, k has to be an integer. For some integer k greater than or equal to 0, right, we can express B as 6k plus 1. So now that's what we wanted to do now. So now if you substitute B equals to 6k plus 1 in this expression, we are going to cancel out the fractions, and that's basically what these last few steps are all about, eliminating the fractions. So let's go back to that and see what we have. We have z squared is equal to c squared plus 3a. Or before this, we might also want to take things step by step, and that's by instead of plugging it in at once, we might actually want to express, okay, since we have A in terms of B and C in terms of A, we can also want to express A in terms of K and C in terms of K, and that will cancel out our fractions just fine now, which is what we wanted. So it actually makes things more efficient. Remember, we are working towards efficiency now. So now we have A is equal to 3B minus 1 over 2, and of course B is equal to 6k plus 1 minus 1 over 2. So of course this is 3 times 6k is 18k, plus 3 minus 1 is plus 2 over 2. And of course this implies that A is equal to 9k plus 1. Fractions eliminated just as we wanted. Let's go to C. We have C is equal to 2b plus 1 over 3, which is equal to 2 times 6k plus 1 over 3, right? So 2 times 6k is 12k, plus 2 plus 1 is plus 3 over 3, and that will give us 4k plus 1. So this implies that C is equal to 4k plus 1. Now we've got what we wanted. We have eliminated the fractions. Now it's just a matter of substitution, right? So we have z squared is equal to c squared plus 3a, which is equal to 4k plus 1 squared plus 3 times 9k plus 1. And this is equal to 16k squared plus 8k plus 1 plus 27k plus 3. And of course this is equal to 16k squared. 8k plus 27k will give us 35k plus 4. Now we have z squared is equal to 16k squared plus 35k plus 4. Now this is what you wanted, right? Why was this important? Why was setting z up like this important? Now because this will help us in bounding z. Remember, just the same way we bounded x with a and we bounded y with b. This will help us in bounding z. Now we're going to bound z with ky, because we can get another square, right, in terms of k. Can get another square in terms of k that is evidently bigger than this. And once we get that square that is evidently bigger than this, we are going to have, is going to force z squared to be less than that squared, which will imply that z is less than that, whatever it is in terms of k. So now this is what we are looking for now. We are looking for this guy here. So now let's again, like we did with a and b, let's take things step by step. So let's try 4k plus 1 is too small. 4k plus 2, that's too small as well. What about 4k plus 3? I believe that's too small as well. And 4k plus 4, let's try 4k plus 4. What's 4k plus 4 squared? Okay, let me do that separately. What's 4k plus 4 squared? That's going to be equal to 16k squared plus 16k squared plus 32k plus 16. Now, how can we compare this with z? It looks lesser than z, right? Let's try this. So let's check if this is lesser than z. We have 16k squared plus 32k plus 16, 16k squared plus 35k plus 4, right? And this will give us 16k goes with 16k, and this will give us 16 minus 4. Is it lesser than 35k minus 32k? And this will give us 12. Is it lesser than 3k? And this will give us k greater than 4, right? So if whenever k is greater than 4, then we can get that 4k plus 4 squared is less than z squared, right? So that's a nice thing we have to have, right? Why? Because now we can now bound z in both directions as well, which is very nice. So we can put a question mark in both places. We can bound z in both directions as well. So now this will help us. So we can assume now whenever k is greater than 4, so let's say for k greater than 4, we have 4k plus 4 squared less than z squared, right? For k greater than 4. Okay, so now let's test z with 4k plus 5 squared. Let's test z squared with 4k plus 5 squared. Remember, now this will help us now to bound z at the other exterior end. This will help us to bound z at the other exterior end. So let's see how it goes, if it's straightly greater than z or not. So we have 4k plus 5 squared to be equal to 16k squared plus 40k plus 25. So now 16k squared plus 40k plus 25, is it greater than z squared, which is 16k squared plus 35k plus 4? Of course, this is true. 16k squared cancels 16k squared, and 40k is greater than 35k, straightly greater than 35k, while 25 is straightly greater than 4. So you are good on this side, right? There's no maybe something with for k, like for in the former case we had for k greater than or equal to 4, right? But this is actually true for all k, since it's true for all k, it's also going to imply that it's true for k greater than 4 as well. So you can also put this into this case and say that this z squared is less than 4k plus 5 squared. Now our bounding is done, right? So I've bounded z at both ends. So now this is going to imply that 4k plus 4 less than z less than 4k plus 5. And this is not possible, right? Because z is an integer, 4k plus 4 is an integer, and 4k plus 5 is an integer. But 4k plus 5 is directly after z, so there's no another integer z. Is between 4k plus 4 and 4k plus 5. So you guys can see why there's a contradiction here, right? So this is going to imply that k cannot be greater than 4, which implies that k is less than or equal to 4. So now, what this bounding helped us do now? Now, instead of bounding z directly, we bounded k. Now, since z is in terms of k, bounding k is going to help us to bound c, which is in fact going to help us to bound c, and then we have which is going to help us to bound b, and then we have c and a in terms of b. So we have bounded k now, so we have k is less than or equal to 4. But prior to this, while establishing k, while establishing k here, you already said that 0 is less than or equal to k. So basically what we have now is 0 less than or equal to k less than or equal to 4. Now we have just how many choices would that give us? Just 5 choices of k, which is 0, 1, 2, 3, and 4. Now this reduces our work a little bit. Now this is the bounding we are looking for. Now we don't need to test for how many cases, right? The problem told us to find all possible cases. Now we are not looking for, we don't need to test for so many cases again. Now we just need to test k equals to 0, 1, 2, 3, and 4. And if any of these cases work, or if all of them work or any of the cases that work will give us our a, b, and c, right? Because k gives us z and z gives us a, b, and c. So let's test it. But first, remember, the first step in testing this is to remember that 16k squared plus 35k plus 4 is actually a square, right? So if you plug in if you plug in k, if you plug in any of this k, 0, 1, 2, 3, 4, if you plug in any of this k into 16k squared plus 35k plus 4, and we don't get a square, then that's a big red flag to tell us that that's the value for k is not possible. But that's not all. We also have to find a, b, and c to see if actually that k works for a, b, and c. But first, let's actually test to see if it actually gives us a square. And if it doesn't, then that's the end of that case. You don't need to go down that line again. But for those that work, then we can now move on to find a, b, and c. So let's do that. So when k is equal to 0, we have z squared is equal to 16k squared plus 35k plus 4. Then this is 0, so we'll have 4 as an answer, and then 4 is a square, right? So we are fine in this case. Then when k is equal to 1, we have z squared is equal to 16k squared plus 35k plus 4, and then we just need to sum the coefficient. 16 plus 35 plus 4 will give us 55. But this is not a square, so that's a contradiction. Then when k is equal to 2, we have z squared is equal to 16k squared plus 35k plus 4, which is equal to 138. Again, this is not a square, so that's a contradiction. And then we'll test for when k is equal to 3. We have z squared is equal to 16k squared plus 35k plus 4. When we plug into here, this gives us 253. And is this a square? No, this is not a square. So again, we have a contradiction. Then the last case, when k is equal to 4, we have z squared is equal to 16k squared plus 35k plus 4. And when we plug in 4, we get 400. Now 400 is a square, so we are fine in this case. So now we have narrowed down k into two choices, right? Which means that k is equal to 0 or 4. Before we had 5 choices, and now we have narrowed it down to just 2 choices. So now we just need to test the two cases. The first case when k is equal to 0, and the second case when k is equal to 4. So let's test our cases, right? We have case 1, and case 1 is k equals to 0. And then, of course, we have b is equal to 6k plus 1, and then 6 times 0 is 0, so we have b is equal to 1. Now we have the value for b now, and then, but also we have a in terms of b and c in terms of b. So now we are going to just plug it in. A is equal to 3b minus 1 over 2. This is going to be equal to 3 minus 1 over 2, which is going to be equal to 1. And then c is equal to 2b plus 1 over 3. And this is equal to 2 plus 1 over 3, which is equal to 3 over 3, which is equal to 1. So you have A, B, C is going to be equal to 1, 1, 1. So let's actually test this to see if it works, right? Because we are not sure if this is going to work yet. So let's test this to see if it's going to work. We just need a squared plus 3b, b squared plus 3c, and c squared plus 3a to be squares. And when we test that, we have a squared plus 3b is going to be equal to 1 plus 3, which is equal to 4, and we are fine. Same with b squared plus 3c equal to 1 plus 3 equal to 4, and they are fine. And same with c squared plus 3a is going to be equal to 1 plus 3 equal to 4, and we are fine. So now that's that for this case. So this is our solution for this case. ABC is equal to 1, 1, 1, and it worked. So this is the solution for ABC, right? So if you actually tested values at the beginning this would have been maybe the first solution we get if we tested values at the beginning, because it's actually very easy to recognize. Just plug in 1, 1, 1, and notice that they are all squares. So that's that for this case, right? So now let's try the second case, the case 2. Let me separate the white screen. Let me try the second case, the case 2. Is k is equal to 4. So now we will have b is equal to 6k plus 1. Of course, this is going to be equal to 6 times 4 is 24 plus 1 is 25. So this implies that a is equal to 3b minus 1 over 2. So now I'm going to have 3 times 25 minus 1 over 2, which is 3 times 25 is 75 minus 1, 74 over 2. We have 37. And C is going to be equal to 2b plus 1 over 2, right? And we'll have 2 times 25 plus 1 over 3. And that's 50 plus 1 over 3, which is 51 over 3. And then we'll have 17. So then we'll have a solution A, B, C to be equal to A is 37, B is 25, and C is 17. And also check, remember, we'll have to check all the conditions in the question. The first condition is A greater than B greater than or equal to A greater than or equal to B greater than or equal to C. And that's fine here because we have 37, 25, 17. And then we actually have to check the second condition, which is the main condition. And that's if A squared plus 3B, B squared plus 3C, and C squared plus 3A are all squares, right? So we'll just have to check that. So A squared plus 3B is equal to 37 squared plus 3 times 25. Now this gives us 37 squared is 1369 plus 3 times 25 is 75 When you sum that up, that's 1444, then which is 38 squared, and that's perfect. Then the second case, b squared plus 3c is going to be equal to 25 squared plus 3 times 17, which is going to be equal to 625, plus 3 times 17 is 51, and when you sum that up, that's 676. So that's going to be 26 squared, which again is perfect. And now we just have one more test case to do and we are done. So 6 squared plus 3a is equal to 17 squared plus 3 times a, which is 37, to give us 289, plus 3 times 37 is 111. And when you sum that up, 1 plus 9, 1 plus, we have 400. And again, this is 20 squared. So this case, both cases, k equals to 0 and k equals to 4, are fine. So we have our solutions, which are ABC equals to 111, and then ABC equals to 37, 25, 17, and we are basically done, because that's it. And this is going to be our solution: 111, 37, 25, 17, and then we are done. So that's it for this problem. This is PAMO 2022, the recently concluded PAMO 2022. This is the problem 2 of the PAMO 2022, the second problem of the first day, and it asks us to find all three tuples A, B, C, such that A greater than or equal to B greater than or equal to C, and A squared plus 3B, B squared plus 3C, C squared plus 3A are all squares. And we solved it, we bounded along the way. I got that these are the only two solutions: 111 and 37, 25, and 17.